Welcome everyone in this video, and today we are going to talk about linear boundary value problem. Linear boundary value problem. So what do we mean by this? See, up till now we have talked about second order, let's say second order equations. Yes, so we stick with second order equations. But the thing is, the data was given only at one point. So basically, we're looking at y at the point 0, y prime at the point 0, or some other point, right? So essentially, let's say up till now, we had this sort of thing. Let me do it here. We have, let's say, the equation which looks like this: y double prime plus y equals to 0. And you had this initial data. Y at the point alpha is, let's say, a, and y prime at the point alpha is b, right? With this initial data, so the data is given at only one point. With this data, you know that there is a existence, there is a like unique solution in whole of R, right? That's what we did because it's, but the thing is, here the data is only given at a single point. Okay, now what we want is we want to see that if, let's say, there are 2 points alpha and beta, yeah, and you know what happens to y at the point alpha and y at the point beta, or y prime at the point alpha or y prime at the point beta. You understand? So basically what I'm trying to say is this: you have the data or 2 points alpha and beta, not only at the point alpha. Clear? Now the thing is this: what can we say about existence of solution, or let's say uniqueness, that sort of questions. Okay? Those sort of questions we want to answer now. Okay, so let's start the class. So what we are going to do is basically we are going to consider the differential equation. So consider this equation. Let's say consider y double prime. So let's take a p naught of x here, p naught of x, y double prime plus p1 of x y prime plus p2 of x y equals to, let us say, for now let's just say r of x, and let's just say that's your first equation. Now this is in some interval I, which is alpha beta. Is this okay? Yes. And of course where p naught, p1, p2 and r is assumed to be continuous in I. This is what our assumption is. Yes, we are assuming they were continuous in I. So together with 1, so essentially we are now putting some boundary conditions. Okay, what are the boundary conditions? So these are the boundary conditions. So what are those boundary conditions? Are L1 of y. This is the first boundary condition. Okay, L1 of y. We will just denote it like this. So please, we are going to use this notation: L1 of y, L2 of y, this sort of thing. So what is it? It is a naught of y at the point alpha plus a1 of y prime at the point alpha plus b naught of y at the point beta plus b1 of y prime at the point beta equals to a. And L2 of y, we will define it as some a b is there, right? So c naught, let's say, c naught of y at the point alpha plus c1 of y prime at the point alpha plus d naught of y at the point beta plus d1 of y prime at the point beta. This is, let's say, b. So a and b. Okay, capital A, capital B. Now here, if this is coefficient, here all the coefficients, a naught, maybe I can write ai is it's better. Here ai's, bi's, ci's and di's are constants. constants for I equals to 1, 2 along with A and B. Along with A and B. It is okay. So everything is constant. Okay. So now see, let's say that, so now whenever we are working with a problem, so basically we are assuming that we have the problem 1, that is always there. Now the boundary conditions change. You see, if why we took it like L1, L2, these are the general boundary conditions. So basically you can take different choice of constants and then you get different sort of boundary conditions. Clear? So first of all, let's just put it this way, that the boundary, the differential equation, okay, the differential equation 1 with r of x is 0, r of x is 0, together with the homogeneous boundary condition, homogeneous boundary condition. Okay. What is the homogeneous boundary condition? L1 of y equals to 0 and L2 of y equals to 0. Okay. So these are the homogeneous boundary condition. It's called homogeneous boundary value problem. This is okay, right? So in this case, A equals to 0 and B equals to 0. This is we are assuming here. Now we look at some interesting issues. So this sort of problem we will call it a homogeneous boundary value problem. Obviously we have the homogeneous equation and then the boundary values are also homogeneous. So A and B are 0. Okay. Now there are many general boundary conditions, but these are the important ones. Okay. So let's just put that important boundary conditions. So please remember these boundary conditions because we are going to use this sort of nomenclature even in the future also. So important boundary conditions. Number A, this is called the Dirichlet boundary conditions. What is Dirichlet boundary condition? This is y at the point alpha is A and y at the point beta is B. Is this okay? That's your Dirichlet boundary condition. So basically you only have data at, basically you need to have data at A and B, right? That's just given to you. So A and B, those are the 2 points where data will be given to you. You have to have, right? The thing is, you don't need to know anything about what happens to y prime. We only know what happens to y. Basically, we know what happens to y at the point alpha and we know what happens to y at the point beta. Okay, that's your Dirichlet boundary condition. Okay, then you have mixed condition, mixed boundary. Conditions. So what are mixed boundary conditions? It is y at the point alpha is A and y prime at the point beta is B. Is this okay? So this is the second boundary condition, which is the mixed boundary condition. Or also one can see that it will be y prime at the point alpha is A and y at the point beta is B. So basically mixed means I have data at the point for y prime also and y also. So basically at two different points alpha and beta I have data on y and y prime. So let's say it is B. That's your mixed boundary condition. Clear? And there is another one which is called C. This is called for now we'll just call it as a Robin boundary condition. Okay. Robin boundary condition. Okay, and what is this? This is maybe it is better to write it as separated boundary condition. Let's not put Robin because separated. Let's just put it separated. Separated boundary condition. What is separated boundary condition? So you have the data at y, a alpha, and the data at beta. Okay, like this: a naught of y at the point alpha plus a1 of y prime at the point alpha is a, and d naught of y at the point beta plus d1 of y prime at the point beta is b. This is okay. Now here you see the data is given like a naught square plus a1 square is non-zero. Okay, again d naught square plus d1 square is non-zero. Why this condition? See, if both the coefficients a naught and a1 is 0, then you do not have any data on alpha, and similarly same thing also for beta also. So you want that condition. Okay, and what happens if you do not have data at one point, let's say alpha, or at the point beta? Then this ceases to be a boundary problem, right? Boundary value problem. Okay, and then a very important boundary condition. This is called periodic boundary value problem. Periodic boundary condition. So what is periodic boundary condition? It is given by y at the point alpha equals to y at the point beta and y prime at the point alpha equals to y prime at the point beta. Is this okay? So basically you know that at the end points the curve comes back to itself such that a derivative is also coincides. Okay, so that's your periodic boundary condition. So now we come to a very definition, which we are going to call it definition. See, we'll say that the problem 1, what is our 1? This problem, p naught y double prime, p1 y prime, p2 y equals to r of x, this problem. Okay, and so maybe let me put it this way, that this is 2. Okay, so the boundary value problem 1 plus 2. So you have the problem 1 and then 2 is the data, right? 2 boundary data is called regular. We call it a regular boundary value problem. Okay, it's called regular if alpha and beta are finite. If alpha and beta are finite, you see this data, this interval alpha beta, okay, that should be finite. Clear? And you need to have this p naught of x is either positive or negative. It cannot have any zeros anywhere, right? So for without loss of generality, we will assume that p naught of x is positive. You understood what I'm trying to say? See, the thing is, if p naught is taking 0 somewhere, in that point y double prime basically does not exist anymore, right? If p naught of x, there is the x naught where p naught is 0, so basically for that x naught y double prime, that first term itself is not there. So basically this problem ceases to be a second order equation and there is an issue there. So we do not want that to happen. So we are basically assuming that p naught x is positive for our problem, actually for the regular thing. Yes, okay. So finite p naught of x is non-zero. Yes, so it can be positive, negative, okay, but generally speaking, we'll assume it to be positive. Huh? Okay, for all x in I. For all x in I. Clear? Yes. So this is A. Then P, the boundary value problem 1 plus 2 is called, this is called, the first one is called regular, right? Now this is called, what is it called? Singular. Singular. If, okay, C, alpha is minus infinity, so there is no lower bound, huh? And slash or, okay, beta is infinity, so it doesn't have to be beta, has to be infinity, either one of them is infinity, okay, and or p naught of x is 0 for some x in I. Is this okay? Yeah. So then we call this problem as a singular problem. Is it okay? So you see, if p naught x is 0 some point, those problem points there is some issue about that second order equation and all. We'll call those type of equations as a singular problem. Okay. Of course, again, if that the interval which we are working with, that is also infinite, so basically minus infinity, infinity, minus infinity, alpha, or alpha infinity, that sort of interval also, if you have the problem, then also we call it a singular problem. Is this okay? Right. So now we are only going to consider, so basically in this whole course, singular problems are difficult to solve, to be very frank with you. Singular problems are very difficult to handle. Okay, generally speaking, we are only going to talk about regular problems. Okay, so our focus is regular problems. Yeah? So the first question is this question: does there exist an unique solution? Unique solution. So basically, first of all, is there exists a solution, and whether that's a unique solution or not, to a regular boundary value problem. We'll just put it like this, for because it's a very big term, I don't want to write it all the time. So this is called regular boundary value problem. Value problem. Is this okay? So we want to know that whether there exists a unique solution or not. Okay, so let's just look at it. See, let's just explore this situation with some examples. So first example is this. So example, see, let's consider this equation, our favorite equation. Okay, y double prime plus y equals to 0, and let's put some initial data on it. So let's say y0 equals to let's say 0, and y at the point pi equals to 0. Okay, so your alpha and beta is 0 and pi. So this is a regular Sturm-Liouville boundary value problem, absolutely no issues there. Okay, and what sort of problem is it? First of all, identify what sort of problem is it. This is called a Dirichlet problem, right? Dirichlet problem. You see, A and B, capital A and capital B, they are going to be 0, and you have data on y only at the two endpoints 0, at two endpoints 0 and pi, right? So this is a Dirichlet problem. Okay, now what is the solution of this problem? Okay, let's do this thing. You see, a general solution y of x looks like a c1 sine x plus c2 cosine x. Now if you put the first data y0 is equals to 0, so basically you get c2 equals to 0, and when you put the other data y at the point pi equals to 0, then also you are going to get c2 equals to 0. So basically here for y, so what is the solution? The solution is this. Okay, for any c1 in R, right? Okay, hence the problem admits infinitely many solutions. Infinitely many solutions. So see, this is a like a huge departure from the theory of initial value problems, right? See, initial value problems, once that initial data is fixed, right, data is given to you, these sort of equations, I know that there exists a unique solution in whole of R. But here what is happening is this two point data is given, and you have like the first example actually shows that they are like infinitely many solutions. Okay, but the question is this: does it always have infinitely many solutions? Yes, let's just look at that. So let's look at another equation: y double prime plus y equals to 0. Same equation, right? Okay, so let's put this data: y at the point 0 is 0. Maybe I can put it 0. Y at the point pi, here I put it to be 0. Let's say I am putting it to be some constant c. Okay, if you want, you can just put it to be some epsilon, doesn't really matter. So basically we are not assuming 0, that's all, epsilon positive. Okay, if we do that, see, it is easy to check, right? It is easy to check. So please check this pattern, that yx, okay, has no solution. No solution. You cannot find a solution. Okay, you cannot find a solution. Now the thing is this again. So basically you see two different data. We saw that with one data there are infinitely many solutions, with another data there is like no solution. And again the C, let's put this data down: y double prime plus y equals to 0. And the second data which we want to prove is y0 equals to 0, and y at the point beta, okay, some beta, I will specify what beta is: epsilon 0 less than beta less than pi. Okay, if this initial data is there, now you can actually show, one can check, one may check that y of x, okay, has an unique solution. Okay, you can easily check this part, right? So please do that right there in general solution, put the initial data and see that there are like a unique solution. I hope this is clear. Okay, so please do that. So you do realize that by changing the data, you can actually see that anything can happen. It can have 0 solution. It can, of course, not anything. It cannot have 2, 3, 5 solutions. That cannot happen, because it's just all of this theory is coming from linear equations, linear system of equations. Okay, so it can have 0 solutions. It can have no solutions. Or it can have unique solution, or it can have infinitely many solutions. Those are the 3 possibilities which it can have, right? Okay, so now, and one thing is, see, for the homogeneous equation, let's say this equation, homogeneous equation, you remember r equals to 0 and L1, L2 is 0, this equation, homogeneous equation, you can always see that y equals to 0 is always a solution. That is always given to you, right? Homogeneous equation. Okay, so now the thing is this, the question is this: for initial data, initial value problem, homogeneous equation, if you are just taking it, it has to have, since the solution is unique, it is only going to be 0 solution. But here, is it the case? Okay, so the question is can one find the necessary and sufficient condition, okay, so that 1 plus 2, one second, 2 is this condition, the homogeneous case. How do I put it? I did not write, I think this one, 3. okay, 1 and 3. So Rx is there, but L1y equals to 0 and L2y equals to 0. This is what we are assuming. Okay, so just an extra assumption, that is okay. One second, what is it? Okay, so necessary condition, so that 1 plus 2 admits has only trivial solution. Okay, one thing, sorry, I should write Rx equals to 0. This is the case, since otherwise if Rx is of course not 0, then 0 is not a solution, right? Trivial solution. So 1 we are considering, but R equals to 0, so basically homogeneous equation, clear, with the homogeneous data. So basically this is homogeneous boundary value problem, that's all. Okay, so our question is this: homogeneous boundary value problem always has a trivial solution, but what is the guarantee that that is the only solution? There does not exist any other trivial solution. Okay, so let's look at the theorem. Theorem 1. What is the theorem? It says that you start with two linearly independent solution of 1. Okay, so let y1 and y2 are two linearly independent solution of 1, okay, with R of x equals to 0. So I am not going to write it anymore, but it is assumed, right? Okay, then the homogeneous boundary value problem HBVP, okay, has only trivial solution. Only trivial solution. What is the trivial solution? If and only if, what is the condition? The condition is, I will write it as delta. Okay, this is the requirement which I am going to use. L1 of y1, L1 of y2, L2 of y1, L2 of y2. This will be non-zero. So basically this C, we know what y1 and y2 is, right? Yes, let's say it is given, y1 and y2 is given. So essentially y double prime equals to y equals to 0 plus y equals to 0. Let's say that's your equation. So you know what y1 and y2 is. y1 is sine, y2 is cosine. You can consider that, right? Now with those two linearly independent, you have the data also. So L1 and L2 you already know how does it look like, okay, with those constants. So you put, you see what happens to L1 when you are putting the sine function. You look at what happens to L2 when you are putting the cosine function, and vice versa. You do that, define that to be delta. If it is non-zero, then you know that there is a trivial solution. The only trivial solution is there. If it is zero, if it only has a trivial solution, then delta has to be non-zero. Okay, the proof, very easy proof. Okay, how do we do it? See, any solution of the equation y double prime p naught y double prime plus p1 y prime plus p2 y equals to 0 takes the form, what is the form? Y of x to be c1 y1 of x plus c2 y2 of x, right? This is the only form which you can take. Now this solves the homogeneous boundary value problem. If you see, this of course solves the equation. Now this has to also solve the initial data, right? So basically, if and only if this solves the homogeneous boundary value problem, if and only if L1 of c1 y1 plus c2 y2 is 0, and L2 of c1 y1 plus c2 y2 is 0. Yes, I think this is clear. Why this has to be the case? Because you see, if L1 of y has to be 0, L2 of y has to be 0. That's the condition. And if y looks like this, then this is true. Okay, so what does it imply? See, L1 of C1 y1 plus C2 y2 will look like this. C1 times L1 of y1 plus C2 times L1 of y2. This is 0. Okay, see, L1 is basically a linear function if you think about it, okay, as a function of y. So we can just break it up. And again, you can write it as a C1 times L2 of y1 plus C2 times L2 of y2 is 0. Clear? See here, if C1 and C2 in y, if C1 and C2 is 0, then y is trivial. Okay, so when does this system this system has solutions, right? When is that solution only the trivial solution? It can have many solutions. When is it only the trivial solution? Okay, when do you think it happens? If the determinant is going to be non-zero, right? So that's the condition. So hence proved. See, C1, there are many different, if the date, let's say if you are assuming that this system, okay, this has a trivial solution, C1 equals to C2 equals to 0, if and only if delta is equals to 0. Delta is this, right? See, okay, the determinant. Okay, so essentially the theorem is proved. So basically it says that the quantity delta has to be non-zero, trivial, very easy to see. Okay, now see, small remark. You see, the theorem which we proved now, okay, the theorem is independent of the choice of solutions y1 and y2. y1 x and y2x. See, y1x and y2x are any two linearly independent solutions. It doesn't have to be any specific solution, so you don't have to worry about it, right? So for convenience, we will assume that you do realize y1 and y2 are any two linearly independent solutions, so they have to pass through some data, right? So some initial data, right? So what we are going to do is this y1 and y2, and one thing you have to remember here, see, whenever I am incorporating that they are linearly independent solution y1 and y2, we are assuming the initial conditions now, right? Otherwise we do not get the linearly independence thing, right? That theory we get it from the initial value problem. So this is why to study boundary value problem also we have to study initial value problem. See, so far for one way we will assume this, that y1 at the point alpha is 1, y1 prime at the point alpha is 0, okay, and y2 at the point alpha is 0, y2 prime at the point alpha is 1. Is this okay? We can assume this, right? Yes. See, initial value problem, right? So see how do we get y1 and y2? If you remember properly, it is corresponding to, so basically the initial data 1 0 and 0 1, right? That's how we deduce the fundamental solution. This is why you can just assume it like this. So y1 and y2 satisfies this particular two data. This is what we are going to assume. So let's look at a corollary now. What is it? So the homogeneous boundary value problem, Okay, let me write it like this, homogeneous boundary value problem. Okay, 1 with Rx equals to 0, with Rx equals to 0, that is plus 2 here, has infinite number of non-trivial solutions, Can you tell us what happens when, if and only if delta is 0? That's trivial, right? See, in this case, what happens if delta is 0, then you can have, there are like infinitely many solutions of this system, right? Then there are like infinitely many solutions C1, C2 such that Y satisfies that equation. So you will have infinitely many solutions, right? So that's if and only if condition, if and only if delta is equals to 0. That's given. Okay. Now let's look at one example of what exactly are we talking about? Example. What can we deduce out of this theorem? So let's look at this equation. Consider this equation: x y double prime minus y prime minus 4 x cube y equals to 0. Okay, and the boundary data L1 of y. What is L1 of y? Let's look at how it looks like for some certain coefficients a0, b0. It will we will consider this y1, y prime at the point 1 is 0. L2 of y is y prime at the point 2 is 0. Is this okay? This is what we consider this equation. Okay, now since okay, so now the thing is, we want to find out if this equation has trivial solution or infinitely many solution or no solution, that sort of question. Okay, so basically look at this. So you see, I'm going to write two solutions out of it, so you can check that whether this is the case or not. Right, so check that y1 of x is equals to cosine hyperbolic x square minus 1, and y2 of x is half sine hyperbolic x square minus 1. This is okay. These two solutions and y1 and y2. So check y1 is this and y2 is this, are linearly independent. Let's just check that part. I hope you can do that. Please do this part, linearly independent. Okay, so first of all, we got two linearly independent solutions. Now the thing is this, you see, and y1 prime, okay, at the point x is nothing but 2x, the derivative of this, and cosine is sine hyperbolic x square minus 1. Okay, and y2 prime of x will look like this. It is 2x, x square 2x, so x cosine hyperbolic x square minus 1. Okay, so that is there. Now the data is given that y prime at the point 1 is 0. So that will imply, this will imply that it is given y1 prime at the point 1 is 0. Okay, so we'll put those data here. So therefore what is delta? Delta is nothing but y this thing y1 L1 of y1 and L1 of y2, L2 of y1, L2 of y2. Okay, so what is L1 of y1? Let's just so it is basically y1 prime at the point 1. Okay, what is L1 of y2? L1 of y2, it is y2 prime at the point 1. Again, L2 of y1, it is y1 prime at the point 2, and L2 of y2, it is, one second, it is y2 prime at the point 2. Okay, now if you calculate it, y1 prime at the point 1 is going to be 0, right? And y2 prime at the point 1, it is going cosine hyperbolic 0, it is 1. And this is at the point 2, it is 4, 3, right? So 4 sine hyperbolic 3. And this one is 2 cosine hyperbolic 3. So this is definitely going to be 4 hyperbolic. So this is non-zero. Okay. So therefore, the problem only have, so this thing, let's call it, I don't know, maybe 3. Okay. So 3 admits only trivial solution. Trivial solution. There is no other solution. Is this okay? Right? So we can prove this part. Yeah? Okay. Right. Okay. So now the thing is this. What about the homogeneous problem we understood. For a homogeneous problem, we have that depending on delta, you can say whether the problem has a unique solution or not. Okay. So now we have another theorem which actually tells us what happens if you have a inhomogeneous problem. Okay. So theorem 2, let's just call that. So the non-homogeneous or inhomogeneous, whatever I want to call it, but anyway, so the problem, okay, let me just put it this way. The regular boundary value problem 1 plus 2 has a unique solution. Okay, this is R not equals to 0. Please remember 1 plus 2, okay, has a unique solution if and only if the homogeneous boundary value problem, so R equals to 0, huh? So R of x equals to 0. Okay, along with those two conditions, huh? So what is it? Homogeneous boundary value problem 1 plus, so Rx equals to 0, that is plus this data, what is, I don't know what I did, what was it, with this 3, huh? Okay, I call this one as 3, so I should call this as 4 and this is 4. Okay, so 1 plus 3, okay, this has only trivial solution, okay. In literature, sometimes this is called Fredholm alternative. Okay, you can have similar sort of results even for PDs. So essentially what it is saying is this: there is a dichotomy between inhomogeneous equation and homogeneous equation. If the inhomogeneous equation, you understand, if that has a trivial solution, if the homogeneous equation only has trivial solution, there is no other solution. Only, see, it can have trivial solution, it can have infinitely many solutions, right? Okay, but what it is saying is, if it has only trivial solution, then the inhomogeneous problem has a unique solution. Okay, so if you want to talk about whether the inhomogeneous problem has a unique solution or not, all you have to check is if the homogeneous problem has a trivial solution. And from the earlier case, we know that when it has a trivial solution, right? So it's all put together. Yeah. Okay. So let's look at the proof. Okay. So what is the proof? So let y1 of x and y2 of x are two linearly independent solutions of the of 1 plus 2, 1 plus 2. Okay, let's just sorry, what am I writing? I should put it together, no? Of this equation, y p naught, because we are dealing with so many equations, so it's getting confusing. Okay, so p naught y double prime plus p1 y prime plus p2 y equals to 0. Let's take this equation. Clear? Okay, and let z of x, okay, be a particular solution of the inhomogeneous problem. Okay, of 1. Is this okay? Right. So then the general solution of 1 can be written as y of x is nothing but c1 of y1 of x plus c2 of y2 of x. You remember, this is that principle, right? That the general solution of the homogeneous problem is nothing but the general solution of the homogeneous problem plus a particular solution of the inhomogeneous problem. So plus z of x. Is this okay? Now see, if this solution, if this solves the regular boundary value problem, right? So, and it has a unique solution. So basically, if it solves the irregular boundary value problem, so the above y solves 1 plus 2 if and only if, okay, L1 of C1 Y1 plus C2 Y2, okay, which is given by, if you break it up, it is C1 times, sorry, this is Z here, I forgot to put that Z here, plus Z is nothing but C1 times L1 of Y1 plus C2 times L1 of Y2 plus L1 of Z. Okay, this is A, and L2 of C1 Y1 plus C2 Y2 plus Z equals to, it is C1 times L1 of Y1 plus C2 times L2 of Y2 plus L2 of Z equals to B. Is it okay? Now you see, this Z is a particular solution, right? Okay, so this is again a homogeneous this is a non-homogeneous system, right? Okay, see, let's just call I4 5. So note 5, the non-homogeneous system 5, A and B are non-zero, right? It's a non-homogeneous system. 5 has a unique solution, if and only if delta is not 0. What does it mean? It means that if and only if the homogeneous boundary value problem, okay, has only previous solution. This is by the earlier theorem, right? Solution. Okay, so you see, and hence it is proved. So essentially what we have is this: when is this homogeneous the system of equation, yeah, when does this equation has unique solution? If and only if delta is 0. right? See, L1 of Z and L2 of Z, these are basically some numbers, right? Huh? For example, let's say L1 of Y is given by Y at the point alpha. Let's just say. Huh? So, what is L1 at the point Z? So, basically it is nothing but Z at the point alpha, which is just a number. So, this equation will look like this. C1, so the delta C1 L1 of Y1 plus C2 L1 of Y2 equals to, you can write it as A minus L1 of Z. Okay, and similarly the other one is B minus L2 of Z, right? So this is some number. So non-homogeneous problem. So when is this equation has a unique solution? If and only if delta is 0, non-zero, sorry, delta is non-zero. Okay, and from the earlier thing, you know, the delta not equals to 0 if and only if the homogeneous boundary value problem only has trivial solution. So basically what we have proved is this: if the inhomogeneous boundary problem value problem has a unique solution, that is an if and only if condition. So basically if it has unique solution, homogeneous problem has a trivial solution. If homogeneous problem only has trivial solution, then the inhomogeneous problem has a unique solution. Okay, right. Now let's look at some example. One example. So consider this equation: x y double prime minus y prime minus 4x cube y equals to 1 plus 4x power 4. Clear? Now we also need the boundary values. Okay, what are the boundary values? So first of all, L1 of y. What is L1 of y? It is given by y at the point 1, and this is 0, let's say. And what is L2 of y? It is given to be y at the point 2, which is 1. This is okay. Yeah. So this is the problem. Let's just call it 6. Okay. Now the thing is this. You can actually show. So please check this part. Check. 6 has only trivial solution. Trivial solution. I hope you can check it, right? How do you check something like this, that 6 only has trivial solution? You just check what delta is. If delta is not equals to 0, then you have trivial solution. Okay, so it's very easy to check. So please do that part. And how do you find y1 and y2? For this problem we already talked about y1 and y2. Where is it? See, y1 and y2. Okay, so you can use that fact. It's not a problem. Okay, use that fact and show that this problem only has trivial solution. Okay, right. Now the thing is this. So if this problem has a trivial solution, what happens to the what is it, the inhomogeneous boundary value problem? Okay, then theorem 2 implies 6, okay, admits a unique solution. Admits a unique solution. Is this okay? 6 admits a unique solution. Okay. Now the thing is this. How do you find such a solution? That question can be answered. Okay. Let's just see how to do that part. Okay. See, the thing is, using the theorem and claiming that there is a unique solution is very nice. But the thing is, how do we get that solution? Let's just try to find out. Okay. So what we do is this. We start with two linearly independent solutions. Okay. So the question is this question. How does one find the solution? Unique solution is fine, but can you find that unique solution? That's the question. Okay. So of course we know that y1 of x, which is given by cosine hyperbolic x square minus 1, and y2 of x, which is given by half sine hyperbolic x square minus 1, are two linearly independent solutions, right? Are linearly independent solutions of the homogeneous problem. That is given. We talked about it just before some time, right? So that is always there. Okay. Now you see, you have to, so you somehow have to, you have to look at this problem and try to figure out if you can, find out a particular solution or not. For this problem, as you can see, that you can use separation of variable, right? So sorry, not separation, variation of parameter, or Duhamel's principle. So we may use Duhamel's principle. I'm not writing that part. You can use Duhamel's principle to get a particular solution, or you can also note. So this is just a observation. Observe that zx, if it is minus x, is a particular solution of xy double prime minus y prime minus 4x cube y. If you look at it, okay, this part is not there. This is minus 1, so it is plus 1, and then 4x cube. So this is 1 plus 4x to the power 4. So it solves this problem. Is it okay? So you have a particular solution. Clear? So therefore, what is the general solution? So what is the general? The unique solution. The unique solution. Sorry, what am I saying? I'm really sorry about it. Y1 and Y2 are two linearly independent solutions of the homogeneous problem, right? Solutions of the homogeneous problem, homogeneous equation. So this equation, without any data or anything, with this equation, x y double prime minus y prime minus 4x cube y equals to 0, right? Subject to some initial data such that they are linearly independent. That's the thing. Now, thing is, we also got a particular solution. So what is the general solution? Let's just say y, general solution of x. And what is this solution is the solution of this problem, right? General solution looks like this: c1 times y1 plus c2 times y2 plus minus x, right? Okay, so that's your general solution. Now the thing is this: we know that there is a unique, this system admits a unique solution. Okay, so we have to find a unique c1 and a unique c2. Okay, so let's look at it. Yes, see, this data is there. Y at the point 1 is 0, y2 at the point 1 is 1. Okay, so see, if you put this data here, so we have y0 equals to y at the point 1. What is y at the point 1? It is c1 y1 at the point 1 plus c2 y1 and y2 at the point 1 minus 1. Clear? And another thing is 1 equals to y2, which is again c1 y1 at the point 2 plus c2 y2 at the point 2 minus x equals to 2, right? So 2. Is it okay? Now, if you write down this equation, this will imply this thing: c1 minus 1 equals to 0. This is what you are going to get, right? So this is y1 at the, you just evaluate what is y1 at the point 1, y2 at the point 1. So basically it is becoming c1 minus 1 equals to 0. And the second part is cosine hyperbolic 3c1 plus half sine hyperbolic 3c2 minus 2 equals to 1. Yeah, this is the two conditions which you are going to get. Okay, now you can of course solve this problem. This is c1 equals to 1. From here c1 equals to 1. So the solution which you are going to get is this: c1 equals to 1 and c2 you are going to get as 2 3 minus cosine hyperbolic 3 by sine hyperbolic 3. This is what you are going to get, right? Okay, so therefore y of x, okay, will look like cosine hyperbolic x square minus 1 plus 3 minus cosine hyperbolic 3 by sine hyperbolic 3, okay, sine hyperbolic x square minus 1 minus x. Okay, so this is what your unique solution looks like, and this is how you conclude that the problem 6 has a solution, and how does the solution looks like. It has a unique solution and which looks like this is how you calculate it. Okay, right. So with this we are going to end this study of linear boundary value problems.